The min-cut problem in single passes through.
Yeah, thanks, Ali. So yeah, like my name says, I'm going to talk about min-cut, and as you might see, there are like a bunch of collaborators here. So let me just tell you a quick story of how the collaboration came about. So Alex and I were working on the min-cut problem in streaming, and it turned out that David and his group had the same set of results, so we decided to merge teams. And yeah, Alex was an undergrad student and he was part of the RU program at Dymax, so we would like to thank Dymax for the collaboration. But okay, so yeah, this is joint work with Matthew Ding at Berkeley and Jelani Nelson also at Berkeley, and Jason Lee, Hong Hao Lin, and David Woodruff at CMU, and of course Alex at MIT. So let's start with the min-cut problem. Right. So you're given an undirected graph, and a cut in a graph is just a subset of vertices, and the size of the cut is the number of edges leaving it. Right? And the minimum cut is the cut of the smallest size. And so we're interested in this problem. And what do we know about min-cut? Right. So in the classical setting, after a bunch of work, Skarger came up with a randomized algorithm for min-cut in Waterloo time. So this is sort of like today's gold standard. We have a near linear time algorithm for min-cut. The only sort of issue here is that the algorithm is randomized, right? So how do we fix it? Okay, so let's use the min-cut max flow theorem. And yeah, it says that the size of the min-cut and max flow is the same. But if we naively try to apply this, we'll reduce min-cut to n max flows. But Lee and Panigrahi say that you can actually reduce them to polylog m max flows deterministically. So this, along with the recent breakthrough for max flow, which gives a deterministic m to the 1 plus little of one-time algorithm, gives an algorithm for min-cut with this time as well. Right? Okay, and final small thing. I don't like this little o font here. Can we get rid of it? Can we get to O tilde m? And note that the tilde over here is hiding polylog factors in n. Okay. And so yeah, it turns out there was this long line of work that de-randomized the methods of Karger, and so they give a deterministic algorithm in O tilde m time. Yes.
So you just what's the? I'm curious, what's the exact setting? So some of these thoughts are not familiar. What's the exact setting here? Is this like a real valued non-negative weights, or?
Yeah. So okay, let's.
Undirected real valued non-negative weights.
Yeah. So let's say an undirected graph, poly unbounded weights and integer weights even. Let's for simplicity.
Okay, but poly and size. So
yes.
Okay, fine. But is it? I mean, is it pseudo-polynomial? Are these methods actually pseudo-polynomial? Do you have a dependence on the magnitude of the weights?
Yeah, I'm not sure actually. I think maybe you can even extend it beyond polybounded weights, but I'm not really sure. But yeah, for us, let's say we focus on this simple setting, undirected graphs, polybounded weights. And for this talk, you can even think of unweighted graphs. So we're going to focus on streaming, which I'll talk about next. But
okay, sure. Sorry, I'm just curious
yeah,
about
of course.
these, I mean, the de-randomization I wasn't.
Right. Yeah, I'm not sure. Maybe we can. Okay, but the question is, okay, we understand min-cut very well, and so are we done? And I want to say we're not done. Because if you look at graphs today, we're dealing with these massive graphs, right? So for example, you have web pages and hyperlinks, or papers and citations, or even social media graphs. And these graphs are so large that classical algorithms fail to address these new challenges. So for example, if your data is stored on a disk, then random access queries become expensive, right? And so we need modern models of computation to deal with these problems. So one way to solve this is just use maybe sublinear algorithms, where you don't query everything, you just query a few, you make few random access queries, and you try to solve the problem approximately. What we're going to focus on today is streaming algorithms, where so information comes to you bit by bit, and you look at the current bit and update the memory using it. And once that goes ahead, you don't have access to it anymore, right? And the goal is to solve the problem after the stream is over just by looking at this memory here. And in terms of graphs, the vertices are fixed from 1 to n, and the edges appear in a stream, okay? And a trivial solution is to just store the entire stream and then solve the problem offline, right? And note that here we don't care about time at all. We're just trying to minimize the amount of space, right? So over here, you would take n squared space in the worst case if you store the entire stream. And like I said, you want to minimize the amount of memory used. And maybe one thing you can keep in your head is this notion of semi-streaming, which says that the memory allowed is O tilde n, right? And again, tilde here is hiding polylog factors n. Okay. All right, so let me just show you a quick example of what it would look like. This is your fixed vertex set, and then you have edges incoming one by one, and you just have, let's say, O tilde n space. And once the stream is over, you just want to answer queries about this graph, right? So only after the stream ends. And just to reiterate that we're only looking at single pass algorithms. You just get to see the stream once. Okay, so let's come back to semi-streaming. So Feigenbaum et al., they defined this model of semi-streaming with the memory budget of O tilde n. And this is roughly close to the number of vertices, but much smaller than the number of edges potentially, right? Because the edges could be like of size n squared. And the reason for this O tilde n is because most graph problems actually require omega n bits of space. Right? So if you look at something like maybe matching or min cut, you want to output the cut, let's say, so that will take you n space. But even for the decision versions, you actually need omega n bits of space. So omega n is really like sort of a lower bound. You want to study space regimes larger than it. And turns out there are many problems that actually admit semi-streaming solutions. So semi-streaming is a good first step. Right? Okay, so the question today is, can we add minimum cut to this list? Right? And okay, turns out you can't. So solving min cut exactly needs n squared bits of space. So you can't add exact min cut to the list. But now the question is, what about an approximation? So just you need n squared bits of space, and you can also store the entire stream in n squared bits. So you can n squared is the right answer for exact min cut. But the question is, what about an approximation, right? Can I get Didelot of n squared space for some approximation, or even semi-streaming space?
So what about something like Kargar's algorithm? Like, can you like sparsify a graph, store only like n over epsilon square edges, and
Right. Perfect. Exactly. So that is the answer here. You can do a cut sparsified in n over epsilon space, a square space. I'll come to it. But yeah, like Anand Guha basically give the a bound, which is again just n over epsilon square in semi-streaming. And I mean, to make it semi-streaming, I have to set epsilon to be constant, or like 1 over polylog n. And yeah, so 1 plus epsilon approximate min cut does admit a semi-streaming solution. Yeah. And the main tool uses cut sparsification, like you said. So let me define what this is. So here you have your original graph, G, and H is some sort of a sparsified graph. So H is a weighted graph on the same vertex set, and it satisfies the following guarantee. It says that if you go over all cuts, right, the size of the cut in H and the size of the cut in G is the same, right? So the weight, size in the undirected case, unweighted case, but yeah, weight. And this is what I mean by approximately equal is this thing over here, which is it's within a 1 plus minus epsilon factor. And the question is, how small can we make H, right? And of course, H can be the same as G, but like Santoshini was saying, you can make it as small as n over epsilon square. And why are we doing this? Because if you can approximately preserve all cuts, then I can just find the minimum cut on the sparsified graph. Okay. So Benzo-Carragher gave the first construction, and they came up with a space of n log n over epsilon square edges. And then Batson, Spielman, and Srivastava improved this and got rid of the log factor. And this is even a spectral sparsifier. We won't be talking about this today, but they even give stronger guarantees. And this is really understood down to the log factors. So Carlson et al. Said that, oh, you actually need the log factor in the lower bound as well. And over here, it's edges, and over here, it's bits. That's why you see a log here and not here. But they say not only for a cut sparsifier, which has to be a graph, they say any data structure that approximately preserves all cuts needs this much space. So the bounds here are very well understood, right? Yes.
So in this, like, is it important? So why are you focusing on the fact that this have n log n epsilon square edges? Is it not important that they can be computed in like this much space?
Good. Okay. This is cut sparsifiers traditionally. Right. I'll just come to streaming cut sparsifiers after this.
Okay.
But my like what I wanted to say over here is actually we don't even care about log factors in this talk. But the goal of this was just to say that cut sparsifiers are really well understood in the classical setting, and people have studied them down to the log factors even.
Yeah. So these are about existence of cut sparsifiers.
Yes. And yeah, good. The question is, can you do something similar in streaming? And turns out yes. So Anand Guha gave an algorithm for cut sparsifiers in O tilde n over epsilon square space. So this answers your question. You can do this, and this solves min cut as well, right? You store the cut sparsifier in the stream. After the stream, just find the min cut on that graph. And we know that any data structure that stores a cut sparsifier needs n over epsilon square space. So we've really solved the cut sparsifier problem in streaming, right? So lower than this space, you can't even solve it in streaming because you can't. They don't even exist. So for cut sparsifiers, the right answer is really n over epsilon square up to polylog factors. But this lower bound does not hold for min cut. So can we do something better for min cut? Or what is the best known lower bound there? So in the same paper, Anand and Guha gave a lower bound for min cut that is n log 1 over epsilon bits. Right? Not a very strong lower bound of n over epsilon square, but n log 1 over epsilon. And maybe this is the right answer. So the question is, can we get a better upper bound, match this lower bound? And Anand Guha conjectured that no, you can't do this. Their algorithm that takes this much space, n over epsilon squared, was really tied for the min cut problem and related problems. And they were correct for cut sparsifiers. It really does need this much space. But we didn't know anything else for min cut. And no progress had been made since their paper. And now let me tell you about our result. So we show that you can actually store a 1 plus epsilon, you can solve the 1 plus approximate min cut problem in n over epsilon space. So we're able to shave off 1 epsilon factor in the space bound. And note that this is on weighted graphs, but we can just think of unweighted graphs for this talk. Right. Okay. So everything up till here makes sense? Okay, good. All right. So this disproves the conjecture of Anand Guha. And note that this stronger sort of upper bound cannot go through cut sparsifiers because they have a barrier of n over epsilon square. And the idea here is that we just need to preserve one cut. We don't need to preserve all cuts, right? So maybe preserving one cut is easier. And this brings me to an object called a for each cut sparsifier. Okay, so let me tell you what this is. So Antoni et al. Relaxed this notion of cut sparsification to preserve just one cut instead of all cuts. Right? So note that this one cut that you have to preserve is sort of arbitrary. So maybe it's hidden from you, but you have to preserve one cut with high probability. And let me be a little more formal. What it means is this. So for all sparsifiers, this is the cut sparsifiers we know. The guarantee is that with high probability, you have to do the following. For all cuts, you have to preserve that value. What for each sparsifiers are saying, I'll just flip the order of these two. So I'll say for all cuts, it is true that with high probability, they're preserved. Right? And this means one is just something here, like we can union bound over polynomially many. So this with high probability is 1 minus 1 over poly n. So you can union bound over polynomially many cuts, and you can preserve polynomially many cuts, but not exponentially many cuts. Okay. And yeah, so this is the definition. And the construction of Andoni et al. Was a data structure of size 4 tilde n over epsilon, right? So they're sort of relaxing this notion of cut sparsification in two ways. Yeah, go ahead.
Does it is there notion of like size information? Like, does it include the min cut is for each?
Good. We don't know, right? So the thing is, it's okay. So what I mean to say is, if you look at a graph and you take for each sparsifier, then the min cut, a specific fixed cut, will be preserved with high probability. But the minimum cut of the for each sparsifier might not be like an approximate min cut of the graph. But yeah, we'll come to those things as well.
In
Yeah,
what
go ahead.
context did Andoni et al. Like construct this data structure? What problem were they trying to solve in this paper?
Good. So yeah. Okay, so let me give you one sort of answer. So some of this, I don't know. I think I don't remember exactly what they were studying, but I guess one of the sort of applications is that, okay, why do I care about this epsilon factor? Like if I'm spending like 10 logs to get down the epsilon factor, does it really matter? Are there applications? And turns out there are some applications where you need epsilon to be like n to the 0.1 or something like that. Like polynomially large, like n to the delta large. And for that, you really need this dependence.
Yeah, small epsilon makes sense. I just wanted to understand, like, I mean, the regular cut sparsifiers have their own applications. I was just trying to understand in what context they were trying to construct for each sparsifier.
Good. Yeah, I guess I'll have to check on that. I don't remember exactly, but we can talk about this offline.
Okay.
Yeah. But, okay. So, yeah, they came up with a data structure of this size. So they sort of relaxed the guarantee in two ways. One is the for each guarantee, but also they're not giving me a graph. And Chu et al., they asked the natural question that, okay, can this be a graph? And turns out, yes, in the same space, I can get a reweighted subgraph of the original graph. So this is really like cut sparsifiers, except you're preserving one cut instead of all cuts, right? So you get a graph as well. And yeah, we for our case, we cannot work with this result. We really need this result, and it might be clear. And the reason is because this is a data structure, this is a graph, but that might become clear later. Okay, so we show that you can even solve for each sparsification in streams in the same amount of space. So with just a few extra log factors, you can solve. You can create a for each cut sparsifier, right? And I will show you how to do this. So we use the sparsifier of CGP18 and we put it in the merge and reduce framework, right? So I will show you what that is right now. That for this we need two properties of these sparsifiers. So let me just pause here for a moment and okay, so is this clear?
Just one question.
Yeah.
I think the previous sketch algorithm, I just didn't completely understand.
So like the difference between these two, or
So the CGP plus 18 is not a streaming result.
no, it's not a streaming result.
So when you said sketch, what does it mean there? Like
Okay, sketch is just, so that's what they call, I think they call it a spectral sketch. A sketch is just, like, it's just a
nothing to do
sparsifier.
with like sketching.
No,
algorithms and
nothing to do
stuff.
with sketching. Yeah.
Got it.
Okay. Yeah, so this is all in the non-streaming classical setting. Yeah, and we show that, okay, you can even extend it to streaming just by adding a couple of log factors. Yeah, and we need sort of two properties. The first property is called mergeability of sparsifiers. So you don't have to like look at the actual math that I'll show you, but intuitively what it's saying is that if I have two graphs G1 and G2 that have for each sparsifiers H1 and H2, right? So if I take the union of the graphs, then the union of the sparsifiers is a sparsifier with the same parameter for the union of the graphs. So H1 union H2 is a for each sparsifier of G1 union G2. And note that over here the edge set is disjoint. And I mean, this is really simple. You just write down the inequalities saying that for H1, the weight of this cut is the same as G1 roughly, and for H2 it's the same, and you just add it up. And now if you look at this part over here, since G1 and G2 have a disjoint edge set, you get that this is just the same as the weight of the cut in G1 union G2. And this is the same for H1 and H2 as well. The second property we need is sort of composability of sparsifiers, which just says that if I have a graph, and if I take a sparsifier, and if I take a sparsifier of that sparsifier, I get another sparsifier of the original graph. Right, so if H3 is a sparsifier of H2, and H2 is a sparsifier of H1, and then H3 is also a sparsifier of H1. Note that if the parameters here are epsilon 1 and epsilon 2, then the parameter here is like 1 plus epsilon 1 times 1 plus epsilon 2. And again, you just write down the inequalities, and this will just pop right out, right? So H3 is close to H2 in terms of epsilon 1, and H2 is close to H1 in terms of epsilon 2, and so you get this. So using these two properties, let me show you what the algorithm is, right? So what is our goal? We want a for each sparsifier in O tilde n over epsilon space and streaming. And first I'll show you this algorithm as a sort of offline algorithm, and then I'll show you how to implement it in streaming. So what do? You take your stream and you break it up into chunks of size k, and k is O tilde n over epsilon. And now I will take the neighboring chunks and I will merge them to give me like H11 here. So this is, if I just merge them together, it will be a sparsifier of size 2k. So then I will also reduce it back to size k. Right? So that's all I'm doing here. So when I get these two arrows on a new block, it means I merge and then I reduce. Okay. And then I keep doing this for log n levels, right? And every time I go up a level, I get another factor of 1 plus epsilon. Right? And the final graph over here is a sparsifier of the entire stream. So this guy is a for each sparsifier of the entire stream below it. So sparsifier of the whole graph. Does this make sense?
So this idea seems very similar to N and Gua's overall sparsifier, right? This merge and reduce idea is very similar to N and Gua's overall sparsifier, if I'm correct. Like basically you have this log n levels.
Right, yeah. So I think the way Anand Guha in their paper gave the sparsifier was not using merge and reduce, but you can equivalently think of the for all sparsifier also in terms of merge and reduce. So I think the AGO9 paper, I think that does not do.
I think one of the papers in this cut sparsifier has exactly the same. If I'm
Yeah. So I mean, this is nowhere in the literature that
this idea would work like in general for like even all sparsifier, right? This is like a very okay.
Exactly. So the only thing you need is this mergeability and reducibility property. Once you have that, you can do it for any sparsifier you want. So you can do it for spectral sparsifiers, like the for all sparsifiers we know. You can also do it for the for each sparsifiers. Okay. And this is not a streaming algorithm yet because you're doing something. So let me show you how to do it in streaming. It's very simple. You keep merging the sparsifiers, and as soon as you have two sparsifiers on the same level, you just merge and put them to the next level. Right? So you keep doing this. Again, you have two, so you put them to the next level, and again. Right? So, yeah. So this makes sense. Good.
So then you might have to have log n chunks in memory.
Right. Exactly. Yeah. So basically, for each level, you might have to keep something.
Yes.
Right? But note that at each level, if I have two sparsifiers, then I will merge them and put them to the next level. So at each level, I can have at most two sparsifiers. Okay? So this will, exactly. So there are log n levels. So the first thing we're going to do is we saw that over here, the parameter keeps growing by a factor of 1 plus epsilon at every level. And we get a parameter of 1 plus epsilon raised to log n at the top. So the first thing we're going to do is sort of set the parameter at the bottom to be epsilon over log n. So you get a parameter of roughly epsilon at the top. And the second thing, like you said, is that there are at most 2 sparsifiers at each level, so you'll have to store log n times these, but it's both of these just increase the space by exactly 1 log factor. And so you get your guarantee of O tilde n over epsilon. Okay, so this gives you a streaming for each sparsifier. Good. Now, how do you use this to solve streaming min cut? Okay, so what was the algorithm of R and Guha? You store the cut sparsifier during the stream, and after the stream, you just find the min cut on that graph. But if we do that same thing here, it might fail. Does anyone see why?
I mean, it may not preserve the min cut because you're preserving only some polynomial many cuts. Why should that be min cut?
Yeah, but those cuts are not okay. You're preserving every cut, right? So if I fix a min cut of the original graph, I know that will be preserved.
Oh yeah. I meant for each specifier that you have, you're not really preserving all the cuts.
Right. So yeah, exactly. So what might happen is the min cut might be preserved up to 1 plus minus epsilon factor. But since there are so many other cuts, maybe some other cut that is not preserved goes below the min cut. And so if I just find the minimum, I might find some other cut that is not the actual min cut or approximate min cut. And we've stored the for each sparsifier in this much space. But this is not enough to solve min cut because we cannot iterate over exponentially many cuts and hope that all of them are preserved. So we somehow need to reduce the search space from exponentially many cuts to polynomially many cuts. And once I just have to deal with polynomially many cuts, I know I can do it using a for each sparsifier because I can take a union bound over polynomially many cuts. Right? So how do we do this sort of reduction? And the idea here is that we additionally store a 1 plus 0.1 for all sparsifier. Right? So this takes O tilde n space because epsilon is constant here. And this is a for all sparsifier, so it preserves all cuts, but up to this value and not up to 1 plus epsilon value. And this tells us what all the small cuts are. So for example, I'm being a little loose here, but it tells us, let's say, what all the 2 approximate min cuts are. And then Karger tells us that, okay, there are not a lot of small cuts in the graph. They can be at most n to the 2 alpha approximate min cuts. So at most roughly n to the 4 small cuts of the graph. So now we've reduced our search space to polynomially many cuts, right? So what is the algorithm? You go over all the cuts. Let me give you a bad exponential time algorithm, right? So you go over all cuts one by one in this for all sparsifier. You only mark the small cuts. And now the small cuts, you go and look at their value in the 1 plus epsilon for each sparsifier. And with the union bound argument, I can say that all of them will be preserved. And so I can pick the minimum out of those. And so I get the minimum. Does this make sense? Yeah?
Is it also possible to enumerate all the small cuts, or just is it an existential?
Yeah. So Karger also gives an algorithm to enumerate all small cuts. So since there are n to the 2 alpha small cuts, you can do it in n to the 2 alpha times log square n, like so O tilde. So it's just a contraction algorithm that will give you these cuts. So you can enumerate them. And yeah, you can do these things efficiently as well. At least it's easy to see you can do it in polynomial time if you have such a thing. Okay, but this finally gives us the O tilde n over epsilon algorithm for min cut. Any questions? Yeah.
So now the bottleneck, the n over epsilon, comes just from the for each sparsifier.
Yeah, because the other component is just O tilde n space. And the question is, is this the best you can do? And turns out for each sparsifiers, n over epsilon is really the right answer. So Antonia et al. They show a lower bound as well. You can't do better than n over epsilon for each sparsifiers. So the question is, can you do better for min cut, right? And it turns out that no, you can't. So we also show that there is a lower bound of n over epsilon bits for solving min cut. 1 plus epsilon approximate min cut, and this is on unweighted graphs even. So we don't need weighted graphs for the lower bound. Yeah, and this resolves the complexity of min cut up to polylog factors. So n over epsilon is really the right answer for 1 plus epsilon approximate min cut. And yeah, like I was saying, this paper also shows a lower bound of n over epsilon bits for each sparsifiers. So that's also the right answer for them. Yeah, and it turns out that these two, like for each sparsifiers and approximate min cut, they're sort of equivalent to each other. You can reduce between them, but it's a small caveat there. Yeah, okay. So how do you prove this lower bound? So let me take a small detour to communication complexity, and that's where the hardness will come from. So you have two players, Alice and Bob, and both of them have an input of n bits, and they want to solve a function f together. And they're allowed to communicate between each other. So Alice is allowed to send a message m to Bob. So Bob looks at the message, his own answer, and outputs the answer. And they also have access to shared randomness. So maybe there are some random bits written in the sky, both of them can look at it. You should think of Alice and Bob as all powerful, but they're limited by this communication, right? So the cost of solving f will be the amount of bits Alice sends to Bob in the worst case. Right, and this is what you want to minimize. So individually, Alice and Bob are all powerful. And what we will look at today is just the index problem, which says that, okay, Alice is given a binary string of size n, and Bob is given a bit, like an index, and they want to compute the bit x of I, so the ith bit of Alice's string. Right? So Alice just sends a message. And you can deterministically show, if you think a little bit, you can show a lower bound of n bits of communication. But we also know that randomized algorithms need omega n bits of communication. So, yeah, this is what we're going to use. This is where the hardness will come from. But the question is, why do we care about communication complexity? Right? We want to prove a streaming lower bound. And the reason we care is because streaming algorithms are one-way communication protocols. So a lower bound in the communication world gives us lower bounds in the streaming world. And let me quickly show you why this is true. Have people seen this argument before? Okay, so let me quickly just run through it. So Alice so Alice sends a message to Bob, and Bob looks at the message and outputs the answer. And so let's say there is a streaming algorithm A for this problem with space S. I will give you a communication protocol with cost S. And so what Alice does is runs A on her input. And the way she does it is by arranging her input into a stream. Then this is the crucial step. She sends the message M to Bob, which is the memory state of the algorithm A. So since A had size S, the communication cost will be S as well. And then Bob continues running the algorithm and outputs whatever the algorithm says. Okay. So what we're going to do is we're going to say that, let's assume there is an algorithm A for 1 plus epsilon approximate min cut that runs in little of n over epsilon space. Right? So it's a streaming algorithm. And we're going to use this to solve an index problem of size roughly n over epsilon. And this is how we'll get a contradiction. Yeah. Okay, so we're solving index and we have access to this algorithm A. So what Alice is going to do is interpret her string as a bunch of disjoint graphs, right? So think of the string S, which is of size roughly n over epsilon. Alice partitions them into chunks of size roughly 1 over epsilon squared. And what does this chunk represent? It corresponds to a graph on a 1 over 10 epsilon vertices, right? So here the number of vertices are 1 over 10 epsilon, so the number of vertex pairs are roughly 1 over epsilon squared. And this part of Alice's input will tell what edges are present and what edges are absent, right? And you can do this epsilon n times. There are epsilon n such graphs. And epsilon n times 1 over epsilon squared gives you S exactly, which is n over epsilon. So this makes sense? Okay. All right. So Alice will run the algorithm A and send her memory content to Bob. What Alice additionally does is also sends the degrees of all vertices to Bob. So yeah, the first part takes little of n over epsilon because of the existence of such an efficient algorithm, and the second part takes just total n.
So these vertices are it's disjoint, like this G1 to
Yes.
epsilon.
Yeah, I mean, okay, yeah. So these vertex sets are disjoint. So all these edges will only be here, these edges will be here. So the min cut of the graph currently is 0. Right? But yeah.
So when you say runs the algorithm on the graph, I'm confused just about the min cut. Min cut is 0, so
Yes, so that part I'll show you. Okay, I mean, this whole thing is the graph G, right? And that is what the algorithm is run on. So currently, if I just run it on these edges that Alice has and ask it for the size of the min cut, it'll give me 0. Okay, but Bob is going to add some additional edges.
Oh.
Yeah. And note that these are not the only vertices. There are some order n other vertices lying around which I've not shown you yet. Okay. So what does Bob want to do? Bob wants to solve index. So he wants to know whether this bit is 0 or 1. What this corresponds to is in some graph GK and vertex pair AB corresponds to does this edge exist or not. Right? So now we're going to fix this AB and we're only going to look at it and try to figure out whether this edge, whether AB is an edge or not. And we're going to do this using the algorithm A and the vertex degrees. Okay, so what is Bob doing? Bob puts A and B on the left side, so this circle just contains A and B, and all the other vertices of GK on the other side. Okay, and Bob observes that if AB is not an edge, right, then what is the size of this cut over here? It's degree A plus degree B. Because all of B's edges go here and all of A's edges go here. Right? Because this side just contains A and B, and since this is a non-edge, then all the edges from A and B will go here, and so the size of the cut will be this. If AB is an edge, then what is the size of this cut? It's this thing minus 2, because 1 degree from A and B will be inside here. Right? So if somehow using the algorithm A, I can ask it what's the value of this cut, then I will know whether AB is an edge or AB is not an edge. Okay? Good. But unfortunately, A just tells me something about the min cut. So let's make this the min cut. Right? And another thing we're going to do is assume that we have an exact min cut algorithm and not an approximate algorithm, and then we'll get rid of this. Okay? So how do you make this the min cut? By adding large cliques on either side. So this is a clique of size, let's say 10n. And these squiggly lines means that every vertex here is connected to every vertex here. So there's an edge between every vertex here and every vertex here. Similarly, these two vertices have an edge to every vertex here. And since these cliques are so large, if I try to move one vertex across the cut, I will get a large cost of like 10n. So this is really the min cut of the graph. Except for one thing, like Santoshni's point, there are these other G1 to G epsilon n. So if over here, if I ask for the min cut, it'll still tell me, oh, the min cut is still 0. Because there are these other disjoint guys. So I just have to attach them to the clique. Right? So take these guys and attach them to the clique again with these squiggly lines. So all pairs have an edge. Now this is really the min cut of the graph. So now I ask the algorithm A, tell me the min cut. If the value is this guy, and since I know the degrees as well, right? See, these are the degrees that Alice had sent Bob. So I know if the answer is this, then AB is not an edge, and if the answer is this, then AB is an edge. Make sense? And so we're done. Except for a few things, but we're done. Any questions here?
I'm a little puzzled about
Yeah.
the reduction, sorry.
Mhm.
I couldn't follow. So, Bob's index, can you again, do you mind explaining what exactly it says?
So Bob's index over here is some I, right? So I know it corresponds to some graph GK. So it's in chunk K. So it corresponds to graph GK.
Yes.
And it is, say, the jth edge in that chunk. So it corresponds to this vertex pair AB.
Yes. Yes.
right? So I want to know if this edge AB exists or not.
Yes, okay.
And that will tell me the value of the index.
I see. And now you're saying depending on whether the edge AB exists or not, your min cut value is going to be different basically. And that's one min cut.
Good. And this is if the graph gives me the value of the min cut. If it gives me the cut, then in both cases it will give me just this cut and then I don't get to learn anything. So let me just make a small fix to that. I'll add a vertex here of degree that is between these two guys. So if this is the min cut, I know that the first thing is the answer, and if this is the min cut, I know the second thing is the answer.
Just to be clear, there is like one large click, all the vertices. So there are 2 clicks or 1 clicks, I think.
There are 2 cliques,
There are 2 clicks. So
one on each side, sort of.
when you say one on each side, you mean Alice adds one of them and Bob? Like, okay. Alice adds
No. Okay. So So Alice just adds the edges within these graphs, G1 to GK.
Okay.
Bob is adding these edges between the vertices and the cliques.
Oh,
and
because Bob knows what A and B are, so
Exactly.
he can like
Yeah.
do this. Okay.
Yes.
got it.
Bob knows what A and B are, so he's going to look at A and B and make the specific construction. Yeah. Okay. And just this is a small thing. You just add this vertex C, which has a degree in the middle. So if the algorithm outputs the cut and not the value, then you can still know what the value of the min cut is. Okay. Good. Except we're not done, and the problem is the algorithm A is not exact, right? So if you look at the cut values here, they're so close to each other, like plus minus 1 even. So if I have an approximate algorithm, this should really break. Right? And the reason it does not break is because this is why we considered a weird disjoint union of small graphs. Because every graph that I considered has size at most 1 over 10 epsilon. So the degrees of A and B are at most 1 over 10 epsilon. So the cut sizes I'm looking at are very small. They have a size only 1 over 5 epsilon. And so if I can have at most epsilon error, then the amount of error I can have in the cut value is just 1 over 5. Right? So the multiplicative error is epsilon times the cut value. And since these cuts are so small, I cannot make any error. And so the approximate algorithm behaves like an exact algorithm for small cuts. And that is why I'm done. Good. So we've solved the index problem in lit law of n over epsilon communication, and this gives us a contradiction. And so we get our lower bound for 1 plus epsilon approximate.
It's very nice that like you don't need to actually. I mean, the lower bound is very strong in the sense of like size. I mean, if it's for example, if you're just outputting cut already, like omega and lower bound is there, but this
Yes.
basically shows that if you're even interested in just size, the value.
Yeah, exactly. Size. Yeah. Good. Okay. So the story of min cut is pretty well understood. So an exact min cut has complexity n squared. Approximate min cut we showed is complexity n over epsilon. But what if we still want to solve exact min cut in smaller space? Can we do that somehow by relaxing the model? Right. So there's this really nice result that if I increase the number of passes by just 1, instead of giving you 1 pass, I give you 2 passes, then I can solve exact min cut in Waterloo space. Right? This is a very strong result, and this was implied by Rubinstein, Schramm, and Weinberg in 18, and Seprasadi and Aditi Dreja. They proved it. They gave a simple algorithm for it in SOSA. So okay, we know this, but again, in this talk, we're sticking to 1 pass algorithms. So can we do anything in 1 pass? And another relaxation that is common in the literature is this relaxation of random order stream. Right, so let me tell you what it is. So over here, the elements of the graph appear in a random order. So note that the adversary can still choose the graph, and the graph is still worst case, but its edges appear in a random order. And maybe there's some motivation that real world data might be adversarial, but maybe not adversarially ordered. But we're interested in it also because this is a provably easier model, right? So for example, maximum matching has strictly better bounds in random order streams. Okay, so let's look at what we can do for our problem. Can we get little of n square space here? And turns out, yeah, we can go all the way to O tilde n space. So if I give you the edges in a random order, then we can output the min cut in O tilde n space, and not only output the min cut, output all the min cuts of the graph in O tilde n space. And note that this is also a bit surprising because there can be n square min cuts in the graph, and the space I'm using is just O tilde n. Yeah. And note that this result works for unweighted graphs, it does not work for weighted graphs. Okay, so this is another strong separation between random order streams and adversarial streams. Okay, so what is the idea? So let me briefly tell you what the idea is, then we'll go into the algorithm in a little more detail. So what we can do is look at the prefix of the stream, and the prefix of the stream is a cut sparsifier itself because the elements are appearing in a random order. So that will tell me what the small cuts are and what the large cuts are. And so in the remaining part of the stream, in the suffix, I can focus on the small cuts and store all the edges that belong to small cuts. And for the prefix, I might have lost information about what all the small cuts are. So what I can do is sort of store a cut sparsifier to not lose this information. Okay. So this is the sort of rough idea, and let me go into this in a little more detail. So let me start with a few assumptions. We'll assume that we know the min cut value lambda up to, let's say, a factor of 2. And you can just easily get rid of this by guessing in powers of 2. This will just give you an additional log factor. We also assume that the min cut size is at least C log n. Because if it's smaller, if it's at most C log n, then we can just store a cut sparsifier with value parameter 1 over log square n. And this will just preserve the min cut. Okay. Finally, we're assuming that the minimum cut is a non-singleton cut. What does this mean? A singleton cut is just a cut where there's just one vertex on one side, and the value of the cut is the degree. And for a non-singleton cut, there are more than one vertex on each side. And yeah, you can if the min cut is singleton, I can just store the degree of every vertex in n log n space and just find the min cut, right? Okay. So with all of these assumptions in place, let's look at the algorithm. Any questions here? Yeah? Okay. Good. So let me quickly tell you what the algorithm is. So you look at the prefix of the graph, and you should think of this as sampling every edge with probability roughly log n over lambda. Right? And Kargar shows that if you do this uniform sampling, then you get a cut sparsifier. But this cut sparsifier might be too large, right? Because if lambda is around log n, this is a lot of edges. This is like roughly order m edges. So instead of storing h itself, I store a cut sparsifier on h with parameter 1 over log square. And since the parameter is 1 over log square and the space is just O tilde n, right? So I can store h1 efficiently. And at this point, I will stop and I will look at h1. And this will tell me what all the small cuts are and what all the big cuts are, since it's a cut sparsifier of the whole graph, right? Okay, good. So what I will do now is for the remaining part of the stream, I will, as soon as an edge arrives, I will ask it, are you part of a small cut? And you can do this by iterating over all small cuts and checking if it's part of any small cut. And so I store all such edges that belong to small cuts.
So
Yeah.
the randomness you're using just because basically the edges you receive are anyway random in the first portion, whatever small portion of the stream, that's exactly your cut sparsifier, is that? Or what exactly is the, how do you get the, is that what you treat as the cut sparsifier?
So okay, if I look at just the prefix, this is a cut sparsifier of the whole graph. And since this might be large, I do this cut sparsifier off cut sparsifier trick to get it to a small space.
Okay.
Right? So that is the sparsifier of the entire graph. And yeah, the only randomness here is in the stream itself. The algorithm itself is deterministic. Right? Okay. And RSW18 tells us that actually the number of edges stored in ES here that belong to small cuts is just order n. And this is why we store a small number of edges here. And this is not true if we consider singleton cuts, and that's why we need non-singleton cuts. Because if you just look at a complete bipartite graph, every vertex is a min cut, and so you'll have n square edges that contribute to singleton min cuts. Okay, but yeah, so we've stored H1 and we've stored ES. Both have a small size of just orbital diameter. Note that the small cuts we have size theta log n. This is because of our sampling rate, right? Of roughly log n over lambda. And so H1 preserves the small cuts exactly in this part of the stream. So if I just look at the graph H1 will preserve all the edges of the small cuts. And ES is explicitly preserving all the edges in the small cuts in the suffix. And so we can find all non-singleton minimum cuts, right? Because their edges are exactly preserved by H1 in the prefix and preserved explicitly by ES in the suffix. Good. And yeah, so we can find all the non-singleton min cuts, and we can also additionally preserve all the edges. So this gives us the final orbital diameter space algorithm for exact min cut. Okay, so let me conclude, and then you can ask me some questions. So we've solved exact min cut in random order streams for unweighted graphs, but the question is, what about weighted graphs? Can we do something there as well? And the RSW result does not hold, so we can't get this property. Okay. Another very interesting question is what happens if the stream becomes insertion and deletions, right? So I'm allowing you to delete edges. Now what can you do for min cut? And turns out you can still store a cut sparsifier in orbital diameter over epsilon square space. This is Anguha and McGregor. And our result shows that, okay, you can't do better than n over epsilon. So what is the right answer between these two? And dynamic streams in general might be very hard. So I can even make the stream polynomial length. So there are two reasons why this is why our algorithm breaks here. One is because if the stream is very long, merge and reduce won't work because there are just too many levels, right? If the stream is of exponential length, there are polynomially many levels. Okay, let's take that out. Let's fix the stream to be polynomial length or even order n squared length. Can I still use this merge and reduce some way to make it work? Okay. And this is all I have for you today. Thank you so much for listening.
Any questions?
I have a question regarding this multipass streams for like min cut 1 plus epsilon. So you mentioned something about a 2-pass algorithm for like exact min cut.
Yeah.
Is there something known for approximate min cut in multipasses? Can you do, let's say, yeah. And also like in terms of if you're just outputting let's say size, is there any reason we should believe? I mean, 1 pass, yes, you proved a lower bound, but in general, is it possible that in multipasses I can actually get a sublinear space algorithm if I just want to output the size of the min cut, or do you think there may be some fundamental barriers to it or something?
Right, yeah, that's a nice question. So if you look at min cut, like I showed in 2 passes, you can solve it exactly in O tilde n space, right? So so like even studying approximate min cut or for like multiple passes, it wouldn't make sense to study it in semi-streaming. But like you said, okay, what about little of n space, right? And I don't know if people have studied this. There's usually this barrier at omega n where if you go to little of n, you are not even storing things for a single vertex. So things become tricky there. So yeah, of course, and now outputting the min cut exactly is out of the window. So what about size, multipass, even approximate size? That is a good question. I don't know if people have thought about it. I don't know if there are low ones, but I have a feeling it might not be easy.
Also, I have a question. So, So what is the motivation behind multi-pass setting? Like, how do people see this setting over versus single pass? And the other question related to multi-pass is like, if I want to show like communication complexity lower bounds there, like, what kind of techniques people use? Like,
Yeah, nice. So, okay, firstly, the motivation for multipass, right? So, streaming traditionally, like, why is single pass really nice? Because if you actually have a stream that's coming in, you don't even have to store the entire stream. And you can just go over it, and yeah, this is why single pass is nice. But if you have the stream stored, what that means is, let's say I have a large graph in my hard drive, and I want to solve some problem on it. Like I said in the beginning, random access queries become very annoying. And so what I can do is just stream over like the whole graph in the disk by bringing it to the RAM. And now the cost of multipass is not really bad. You have the stream stored, so you just want to like make one more pass. It's like 3 times or 4 times as worse, whatever. Like you just have to get the head back and go over it again. It's not that much more costly to begin. So multipass is interesting when the stream is sort of stored. Okay. And you said, how do you prove lower bounds? Yeah. Right? So, like, okay, we use index. Index goes out of the window because in the second pass, Bob can just. So you're trying to look at these communication protocols. So at one extreme, you have communication where you're not restricting. There's two-way communication between Alice and Bob, and you're not restricting the number of rounds. And the other extreme is what I was talking about today, is one-way communication, where Alice just sends one message to Bob, and Bob is never able to communicate with Alice. Now people look at, okay, what happens if I allow just k rounds of communication between them, right? So I think if you look at some maybe pointer chasing, that in k rounds you can do it easily, but in k-1 rounds it's like sort of hard.
Cool, great. So let's thank the speaker again.